Let's say I introduce our next speaker is Marek Golasiński from University of Warmia and Missouri, Poland, and the title of is Octonionic Stiefel manifolds and vector bundle. Please.
Okay, thank you very much. Dobry ranek, good morning to everybody, and I was sorry, I late. The problem was that I had problem with computer, but my colleague did it at the best, and probably would be okay now. Okay, so first of all, I would like to thank to organizers for inviting me for next AGMA, especially my great thanks to Sergi, who I was in touch about this conference. So the title of my talk is Octonionic Stiefel manifold and vector bundles. But doesn't work. Now is another problem. I don't see, I cannot move to next slide. Oh, now it's all right. Okay. So this talk is based mainly on the following joint book with Francisco Gomez Ruiz from Malaga University in Spain. And the title of this book is Grassman and Stiefel Varieties over Composition Algebra. This book is appeared last year. Okay, so let's start from abstract of the talk. Algebraic set, polynomial, and entire rational maps are studied in algebraic geometry over any field. But in the case of reals, they have rather special behavior. The fact that there are non-constant polynomials without zero gives the rise to our entire rational function, which are everywhere defined and are not polynomial. It is known that many elements of homotopy groups by MSN, with any sphere, can be represented up to homotopy by algebraic, i.e., are anti-rational, but there is real numbers, maps for any n sphere. To reach that, some advanced methods from the differential topology are applied. We aim to concentrate on the problem of map from SM to SN and about representing such maps with the codomain S8, S8 by anti-rational maps. First, we fix up some background and recall some necessary results as well. Okay, so let's make some excursion to history. Real number divised algebra. The Frobenius theorem, proved by Frobenius in 1877, characterized finite dimensional associated divisor algebras over real number. According to that theorem, every such algebra is isomorphic to one of the following: reals, complex, and quaternions. These algebra have real dimension 1, 2, and 4. Of those three algebras, R and C are commutative, but H is not. But this H is associative. Also note that H is not C algebra. There is also Pontryagin invariant of characterization of those algebra. So if D is connected locally compact division ring, then this ring D is one of the field of the object which we considered before. So namely reals, complex number, and quaternions. This theorem is closely related to Hurwitz theorem, which states that only real normal division algebra are RCH and the non-associative algebra of octonions. Octonions satisfy a weaker form of associativity. Sometimes it's called Mumford laws. Namely, they are alternative and power associative only and are not as well known as complex number and quaternions, which are much more widely studied and used. Octonions are not as well known as quaternion and complex number, which are much more widely used, but they have application in fields such as string theory, special relativity, and quantum logic. Furthermore, octonions are related to exceptional structure in the mathematics. Among them are simply connected compact exceptionally groups, G2, F4, E6, E7, and E8, being useful for the classification of connected compact Lie groups. We point out that this result has been extended to formally real closed field as well. So reals could be replaced by formally closed closed field, and still we have the same characterization of object as real, complex, and quaternions and octonions. The fundamental object of study in algebraic geometry, algebraic varieties, which are geometric manifestation of solution of system polynomial equation. Because of Hilbert's theorem, it is based on algebraically closed field main. Real algebraic geometry is a sub-branch of algebraic geometry studying real algebraic set. Many classical objects in differential geometry may be described as matrix real algebraic set. Now we concentrate on Stiefel and Grassmann manifold mainly. So we start from Stiefel manifold. So let F be denotes real complex numbers or quaternions. Recall that Stiefel manifold, which will denote V sub n R F, where R is less equal n, is the set of all orthogonal R frames in F to power n, which can be thought as a set of n times k matrices by writing a frame as a metric of k column vector. We then have that Stiefel manifold could be identified with a set of matrices n over R, such that conjugation of R and its transposition multiplied by R is identity matrix IR. Okay, so by analogy, we define also Stiefel manifold for octonions in the same way. So this is the same set of matrices and over R over octonions, such that the matrix satisfies the same relation as for F, where F is R, C, or H. But each V and F, where F is real complex, completed quaternion, can be also described as homogeneous space. Namely, that is the quotient, it is a homogeneous space but unitary matrix over n of dimension n by n and divided by subgroup of unitary matrix n minus r minus a square matrix over F. But for Stiefel manifold over octonions, we cannot do this because we even cannot dream that we have a group of unitary matrices. But we have some result about this set. Namely, that you can show that the real dimension of Stiefel manifold over octonions is equal to A and R minus 4 squared plus 3R. And this view and RO is a compact smooth submanifold of a manifold of matrices n over R for any R less than. Also, we can show that this Stiefel manifold of octonions is path connected. And we can define a map from V and R plus 1 to V E and R such that the value of this matrix, so this last column is written as a V, is simply the value of P. The value of P on the matrix where the last column is V is simply equal to matrix A. And this map is a smooth free bundle. And also we can show what is the fiber of any point, namely preimage of A is equal to set of matrices, such that you can see that there's some relation. So about this fiber, you can show that it's a unit real sphere in the real vector space, which is the kernel of the matrix A bar T. The bar is for conjugation, and this sphere has dimension 8 times n minus r minus 1. Grassmann manifold is differential manifold that parameterizes the set of all r-dimensional linear spaces of N. Since the real and rank of orthogonal projective operators is equal to its trace, we can identify Grassmann manifold over F. F, let me recall, that is real, complex, or quaternions. It is a set of matrices, of square matrices, such that A is equal to A bar T, so such matrix sometimes is called Hermitian matrix, and is equal to A square. And trace of A is equal R. So, by analogy, we can define Grassmann manifold over octonions. So, it's a type is copying word by word what is given for F. So this representation determines on G and F and on the Grassmannian on F and octonions algebraic varieties over R, because we have some algebraic relations. But for F, Grassmannian is also homogeneous space. So it is a quotient of unitary matrix, is n by n, and divided by product of square matrix R by R, by n with other subgroup of matrices is unitary matrix n minus R and square matrix. So, but for F, also we have principal UR bundle. So the fiber it is unitary matrix, that is group of unitary matrices is R over R. Then we can include to Stiefel manifold in R, and the quotient is Grassmann manifold. But due to non-associativity of octonions, we don't have a Stiefel map, as we have for real, complex, and quaternions. So that is, but we are doing our best to overcome somehow this problem. So that the way which we propose is following. So consider subset of a Stiefel manifold, which we denote V prime and R, and this set is defined as follows. So matrix belongs to this V prime if the set of all entries of A generate associative sub-algebra of octonions. Then we have, so for V prime, we can define Stiefel map for V prime and RO to G and R, given in such way that value of on A is equal product of matrix A times the conjugation of A and transposition. So similarly to V prime, V and R O prime, and we define G prime and O as follows, that the matrix belongs to G prime and R if all entries of A generate associative subalgebra of O. It is clear the Stiefel manifold, which we define above, from V prime to Gn, is a surjective map from V prime to G prime. So in particular, we can show that G prime and RO is piecewise smooth path connected.
Marek, may I ask you a question?
Yeah, of course.
This associative subalgebra, so it is isomorphic either to R or C or quaternions. Yes.
Exactly. Yeah.
And so it is. So there is some, I don't know, some splitting of this space into matrices which generate only R or generate only C complex, or so is there some, or this is like simplification?
No splitting, but I say more. If it's generated by R or C, then R and C could be included to octonions. So in the rest of talk, we assume that this algebra is simply isomorphic to quaternions.
No, I maybe not. So this is like, I don't know, CW partition or something like this. So those matrices will generate on the R and will generate on the C, or it is hard to say what
We
is.
didn't study this. We only assume that this is associative algebra, and but so could be of course reals, complex, or quaternions. But if it's R on complex, then this algebra could be included to some quaternions. So we assume that we consider such matrices for V prime and G prime that generate some algebra which is isomorphic to quaternions. We didn't study this. We didn't study this case for R complex number and Q separately. So we concentrate only that we need some ideas which are for quaternions. Sorry, which are for quaternions, because we are looking for associative case, and that is why we define G prime and G prime in such a way.
But maybe also if you consider only subsets which generate R, then this might be some submanifold. So you might get some partition, CW partition or cellular partition, something like this.
I think you are right, but we did study this.
Okay. So thank you. Yes.
Yeah. Lemma. Okay, so this is so lemma is following. The unit sphere S8 and Grassmann G2 and 1 over octonions are algebraically isomorphic. That is, there is entire rational bijection from S8 to G2A such that the inverse of this map is also entire rational. And the proof is quite simple. So using the definition of Gn Grassmannian Gn over octonions, you can show that this octonion is given by matrices such that on diagonal are alpha 1 minus alpha, where alpha are reals, because this matrix is Hermitian. And the rest, the other two elements are given by B and B bar, where B is any octonion. And also there are some relations that modulo of beta square is equal product of alpha times 1 minus alpha. And this map phi is defined in the following way. So the first notice that S8 could be represented by pair of numbers, alpha beta, where alpha belongs to R, beta to octonions, and such that is following alpha relation. Alpha square part modulo of beta square is 1. So value of phi O on this pair, we define a following. That is 1 over 2, and it's the matrix when the diagonal is 1 minus alpha and 1 plus alpha. And the rest is that the other two are defined by beta and B and conjugation of beta. And on this matrix, you can show that this matrix is G2 and plus 1. Then this map is polynomial, and its inverse is given the following way. So if you have any matrix from G2 plus 1, G2, comma 1, then value of inverse is pair 1 minus 2 alpha to beta, where A is any matrix from G2 and plus 1. And you can show that that composition is identity of this matrix. And we have another proposition. So first, suppose F is a real, complex, or quaternion. Then we can show that, that is probably well known, that Stiefel manifold G n comma n over F is the same as unitary matrix. So unitary is over. So this usually use this name for complex. No, but for quaternions, people sometimes uses denoted by SP. But to unify where we use the notation UN. But one has to be careful with UN over quaternions. UN over quaternions could be defined because we have notion of conjugation, transposition, but UNO is not a group because it's not associativity. But this set could be defined. Now here we have definition. So this set of matrices n over octonions such that the product of conjugation and transposition of A is the same if you change the order, and that is identity matrix. But okay, and also we can consider U and O as a set of matrices, square matrices over octonions and over R, such that the product of conjugation transposition of A is IN. And we have the following example. So if we consider matrix, which we see on the screen, then we can show that this matrix belongs to a Stiefel manifold V2, 2 over octonions. But in general, transposition and conjugation of this matrix is not in the Stiefel manifold V2, 2. So we can show that this is the product of A and transposition and conjugation of T is I2, if only if this product ABC is associative. So namely, A times BC is the same as AB times C. If we have also other properties that V prime and over octonions is contained in UN, and UN is contained V and O. And also we can describe this U and O, this is not a group, there's only a set, as intersection. No, I'm so sorry again, but I have technical problem. So I was disconnected. So let me find it a place where we stop. I think that we are here. Okay, so we define V prime and G prime, and there is a theorem which shows that in the low dimension, G prime to 1 O coincide in G to 1, and that is S8, and this 8 is, of course, diffeomorphic to K line, the OP1. And the same for G prime 31 over octonions, that is the G31, and the same for G prime 32, and that is, of course, the Kelly plane. So we have good news that for low dimensions, we have equality. Okay, but in general, we have inclusion that G prime is that V prime is contained UN, and this is contained in V and N. Okay, and this proposition probably it was before, then I don't want. Okay, so we have following fact that although U2O coincide in V prime to 2. So from this is follow that D2O is path connected. But we have conjecture that U and O coincide in V prime and N for any N. Okay, and now we move to vector bundles over octonions. Sergiej, słyszysz i słyszeć?
Yes, yes, yes.
Okay. So we are moving to vector bundles over octonions. So first, none of reasonable sources except Georgian paper, which was published in Advanced Mathematics 2017 and indicated by Sergiej, related to the subject are unknown to speaker. Therefore, great thanks in advance for the audience for possible comments and suggestions. So we are trying to do something in vector bundles which we could find in literature. By analogy with real, complex, and quaternions vector bundles, we define octonion vector bundles of rank R over some space S as a continuous map from X to G prime dash RO, which by definition is the union of G prime and R for sorry, should be opposite opposite inequality. So for n less equal n. And also we recall that some natural F vector bundle for F were equal to reals, complex number, and quaternions. There is a triple where this total space is given by set of pair AX, which is in the A belongs to G and R, and X belongs to F power n, such that AX equal X, and pi, a value of pi at the pair X is equal X. Furthermore, for the rest of the talk, we need some result. Stated in the book by Bochna, Koster, and Roy about real algebraic geometry. And this paper, this result also appeared in the paper by Bochna and Kuchasz, Algebraic Approximation of Mapping into Spheres. And this paper was published in 1987 in Michigan Mathematics. Namely, the theorem is as follows. Let X be a compact, non-singular, real algebraic set, and let F be a map from X to G and F, indices be smooth. Then the following conditions are equivalent. F can be approximated in C infinity topology by the entire rational map from X to G and R, G and RF. F is homotopic to entire rational map from X to G and R. And the pullback smooth F bundle, F star, which is the pullback it takes gamma and R we defined before, is C0 isomorphic to a strong algebraic vector bundle over X. And we are going to use to make use of this and to state some result we are looking for. Finally, adopting the proof of the result above, the following theorem could be shown. Any smooth map from X to G prime and R of O with R less equal N and X a compact non-zero algebraic set is homotopic to entire rational map from X to G prime and R O. Then we derive that any smooth map from X to G prime and RO with N equal 2 and 3 and R equal 1 is homotopic to entire rational map from X, G prime, and RO. In particular, we deduce that any continuous map from N sphere to SA is homotopic to entire rational map. Because for N equal 2 and 3 and N equal 1, G prime coincide with G without prime. So in other words, these matrices in G prime, the entire entries of matrices of G and R generate associative subalgebra of O. Then the method which was used in theorem, which we referred to before slide, could be adopted in this lower dimension. Okay, and then this is the end of my talk. So thanks a lot for your kind attention. Thank you very much for inviting me to attend this next AGMA conference. And I'm so sorry for a number of problems. So I would like to overcome this, but sometimes I was unable to do it. Thank you very much once again for your attention.
Thank you, Marek.